Do you know how to plot deflected shape of structural frames? Understanding structural behavior is a key skill that every structural engineer should have. In this tutorial, I will solve one example taken from the Institution of Structural Engineers certificate course on structural behavior. So let us dive into today's lecture. If you're new here, I am Dr Jawed Qureshi, a senior lecturer at University of East London here in United Kingdom, and on this channel we explore civil engineering and human skills to help us lead more productive, happy and examined life. This is the question which I've taken from IStructE's structural behavior certificate course. What is the correct deflected shape under the loading for this frame? This is a frame where you have a simple support on left side and a roller support on right side, and a central point load is applied. Assume that flexural rigidity is constant. It means that Young's modulus and moment of inertia is constant for all the members. There were 4 options for this question, and I'm quite amazed how my viewers have taken these options. I have posted this question in my community tab a couple of days ago, and I was quite surprised that I didn't get the right answer. Then I thought to make a video so that I can explain this to engineers and students who struggle with understanding the basic behavior of structures. There are 4 options here, and here I will be using qualitative analysis to come up with the solution. No calculations are required, but here we have to understand basic rules in order to solve this problem. And the answers which are here, they look pretty much similar, and it's very difficult to decide which one is correct answer, and you will know in a minute that which answer is correct. I strongly suggest that you take this quiz by scanning this barcode or going to this link before you watch this tutorial, so that you know that where the knowledge gap is, what is missing, and then you can fill that knowledge gap by viewing this video. If I click on this link, it will take me to the tutorial. Because there wasn't any option for 4th option here, so I just included 3 options, and here you will be surprised that how many people have got it wrong, but it's not a big deal. Everyone can get it wrong. In fact, I got it wrong when I was attempting it for the first time, so don't worry about it. We will sort it out. If I choose option 1, then you can see that most people, they are thinking that option B is correct, and we will find out in a minute that which option is correct. So bear with me for a few more moments. For understanding these problems, first of all, you need to understand the basics, and there are a couple of things in this basics. First is moment is equal to force times perpendicular distance. So if I'm applying moment here, the load has to be perpendicular. In that way it will bend. And for deflected shape or deflected form, we need to know 3 things, and these 3 things are support conditions. First of all, what kind of support is there, position and magnitude of all applied loads, and more importantly, joint compatibility. And I'll explain in a minute what does it mean by these 3 factors. First, support conditions. You need to know that what support conditions are there. So for example, first one, roller support horizontal. It can move in horizontal direction, it can rotate as well, but it cannot move in vertical direction. How about vertical roller? A vertical roller, it cannot move in X direction, but it can move in Y direction, and it can rotate as well. A pin support, on the other hand, It cannot move in horizontal and vertical direction, but it can rotate. A fully fixed support, on the other hand, it cannot move in horizontal and vertical direction, and it cannot rotate as well. And finally, vertical support. This kind of vertical support is known as a prop. So when we have continuous support, we put some kind of props under slabs in real life, and they can be treated pretty much similar to what you have in a roller support. So here it cannot move in vertical direction, but it can move in horizontal direction, and it can rotate. So keep these things in mind. That will help us plot deflected shape. The second most important factor is loading. In loading, if we have a point load, the shear force diagram will be drawn like this, and the diagram will drop immediately where you have a point load. And bending moment diagram will consist of only straight lines. If you have, on the other hand, a uniformly distributed load, then shear force diagram will cross the line and there will be a point of zero shear force. And at that point of zero shear force, we will have bending moment max. And here it will be drawn as a parabola or 2-degree curve. How about if you have a uniformly varying load? In that case, you will have a 2-degree curve in shear force diagram, and in bending moment diagram you will have a 3-degree curve. It's very difficult to distinguish when you are drawing it with hand what is 2D and 3-degree curve, but if you're drawing it with a CAD software, certainly it will make more sense. How about if you have a moment applied at a point, then shear force will simply be a straight line, and wherever you are applying moment at that time, the bending moment diagram will switch sides and it will have a diagram like this. So keep these things in mind: support and loading. And our third one, and the most important one, is joint compatibility. In joint compatibility, when you have a fixed joint, which is here, it will maintain its 90-degree regardless of loading applied. Whenever you are applying loading, the members will deflect, but the joint will maintain 90-degree. Here you can see that when you are applying loading, the member is deflecting and this member is deflecting as well. Here you can see that because of fixed support, there is no rotation when the member is deflecting. So all members remain connected and rigid joint remains rigid at 90-degree after it has deflected. So keep this thing in mind. 90-degree is very important. So this is termed as joint compatibility. So joints have to be compatible. Now I will use qualitative analysis to come up with deflected form, which means that no calculations or very simple calculations are required. These kind of problems are inherently very difficult to solve, and the reason is that there is no direct solution to them and they seem open-ended. So whenever you see all the options, you feel that these options are actually right, but there are subtle things which you can use to come up with the correct answer, and then you will demonstrate understanding of structural behavior. For qualitative analysis, the solution is three-part. First is deflected shape or form, and then you draw bending moment diagram, and then you come up with reactions, at least the direction of reactions. In this way, you will be able to understand the behavior of structure without overly relying on computer software. Now, there are certain golden rules that you need to follow to come up with solutions. First is bending moment is always zero at internal pin or a simple support. Here we have internal pin at point D, and at D you can see that we don't have any bending moment at all. And at point A, you have a pin or hinge support where you can see that bending moment is 0. So bending moment is always 0 at simple or pin joint or internal pin, and also it is 0 at a roller support as well. Second is bending moment diagrams cross the baseline at points of contraflexure. Points of contraflexure means that there is no moment at all. So imagine there is a pin over there, so there is 0 moment, where a moment cross line from a hogging to sagging moment. Hogging moment means tension at top and compression at bottom. Sagging means that tension at bottom and compression at top. Here you can see at joint A we have a fixed support, and when we apply load W, you can see bending moment diagram is changing direction, and we have a point of contraflexure, and this is a point of 0 bending moment. You can see it is a kind of pin. So wherever the bending moment diagram is changing the direction, at that point we have points of contraflexure. Another rule is that bending moment diagram under a uniformly distributed load is always curved. We will not have a line here. So here you can see we have uniformly distributed load, and BMD, bending moment diagram, is a curved line. So remember this rule as well. And at a fully fixed support, the deflected shape must show 0 rotation at the face of the support. So it means that there is no rotation. So when it is deflecting, it is completely connected over here. There is no rotation shown. If it was a pin, then you will see that rotation will happen. There will be some degree of rotation, but because it is fixed, whenever you are plotting a deflected shape or form, then you will show a 0 rotation at the face of the support. So remember this rule. If loading is a point load, BMD, bending moment diagram, will consist of straight lines. So whenever you are applying a point load, the bending moment diagram will be straight lines. It will not be curved. Curved will only be in case of uniformly distributed load. Now let us come back to the question. Now once the basics are clear, then it's easier to solve the question. Now option A looks fine. We have a roller support here. When we are applying loading, certainly roller support is going to move rightwards. We have 90° here as well after loading applied, and we have 90° here as well. And because of pin support, you can see this side is rotating, which is fine as well. Now one thing which is little bit off here is that when we are moving one member which is connected with roller support to right side, what is stopping these top joints from moving rightwards? And the answer is nothing. So nothing is stopping them from moving rightwards. And when they will move rightwards, then deflection in column will not happen. So here this column is deflecting. If you say that here I have a pin support instead of a roller support, then I would say yes, it will deflect like this. But when there is no pin support at right side, then the chances are that when right support is moving rightwards, then what is stopping the left column from moving rightwards as well? Because here they are connected at the top. This answer, based on this logic, this answer is wrong. When one part is moving to right, what is stopping the second column from moving right? So the structure cannot behave in isolation. The structures are connected together, unless if there was some kind of force which was stopping it from moving rightwards, which is not the case here. So in my view, this option is incorrect, and there were 14% votes for this option. Now let us assess the second option. In second option, immediately when you look at it at roller support, when you are applying loading, roller support can move right or left. When you apply loading, almost certainly it will move towards right. But here, deflected shape is not showing its movement, so it's not moving at all. So when it's not moving at all, it means that this option is incorrect. Now you will say, in what situation this option can be correct? In one situation this option can be correct, that if you replace this roller with a pin support, then in that case this deflected shape is fine. But here, because we have a roller support, that will cause it to move rightwards, and here I cannot see any translation at this support. It means that this option is wrong as well. And almost 64% of votes, they went to this option B. In option C, it didn't have much votes, I think probably 10-12%. Roller support, when load is applied, roller support is causing it to move rightwards, and then there is a 90 degree over here, and there is a 90 degree over here as well. So it satisfies the joint compatibility, it satisfies the support condition, and the loading condition. Yes, when you are applying downward load, it should deflect like this. So because this roller support is moving rightwards, it is causing this column to move rightwards as well, without any deformation in the column itself. Because when it's moving rightwards, the downward force is not causing any deformation. If it was stopped, then it will cause deformation in the column. So deformation in the column should not happen if one support is moving rightwards. So this is the correct answer. So I will put a tick on this answer. This option C is the correct answer. Now how about option D? So it will automatically eliminate option D. In option D, now these two options are very close. Now you have to be very careful in seeing the subtle differences. Here, this is moving right, this is fine. No deformation is happening in this column, this is fine. When load is applied over here, now you would see that some kind of deformation is happening over here. Now, when the right column is moving rightwards, left column should not have any deformation. When it has some deformation, it means that this option is wrong as well. This is 90 degree, this is fine, and I think that here angle should be 90 as well, but the deformation should not happen here. Now in what situation it can be possible that we have this deflected shape? In situation where, for example, this load is 20 kilonewton. 20 kilonewton means 2 tons. That is roughly weight of any SUV car, Lamborghini Urus or any other SUV. And if there's one point load applied, for example 20 times less here, 1 kilonewton, that might cause little bit of deformation over here, and the deflected shape might look like this. But for our condition where we just have one point load, vertical one applied, this option is completely wrong. So correct option is option C. I will go back again to the quiz question and show you. Here you can see a whopping 67% of people, they thought option B is right. I couldn't put option D in YouTube because there weren't any more options, and option C, only 60% of people said it's right. In fact, the option C is the correct one. So we learn from each other, and I will explain in future tutorials as well how do we understand structural behavior. Now, once you have understood these questions, you are ready to draw the deflected shapes of these diagrams, and I've taken it from David Brown's book, Understanding Structural Behavior. So you can apply qualitative analysis by drawing the deflected shape, drawing the bending moment diagram, and working out the reaction, at least the direction of reactions. Here I've just covered the deflected shape. In my future tutorials I will cover moments and reactions as well. Thanks for watching this tutorial, and I will see you in my next video. Thank you. In today's lecture, I'm going to talk about deflection of beams and frames. Understanding how beams deflect is extremely important, and it is part of understanding structural behavior. If you understand how structures deflect, the chances are that you're not going to make any mistake, even if you're using